Thank you. It's always nerve-wracking to have the stage, right? It's like you get up there and you're stepping onto the stage and like, here I am. So here I am, except I'm on a little blip and it's somebody's computer screen rather than actually stepping on stage, but totally fine. Okay. So if you have read my abstract, it says something about like playing around with these factoriadic happy numbers, and then I'll prove something or give an outline of a proof. And I decided the last minute that I'm not going to do the outline of the proof. We're just going to play around with factoriadic happy numbers because you know what? It's more fun. Okay. So anybody who wants to read the proof or look into the proof, you let me know and I'll be happy to provide you with the paper. We can go every detail of that proof. But for today, we're just going to play around with it a bit. Okay. So, but before we start that, I'm going to tell you just a little bit about myself because I always find it so interesting to hear about where other mathematicians are coming from and who they are and what, their lifestyle is like. And so I'm going to tell you a little bit about me. So here is a little montage of me. So you can see my husband and I, going out hiking. You can see my eldest daughter with a chicken on the door of our car. You can see my youngest, who's still a little bundle of joy, who happens to be downstairs desperately wanting her mama, but she'll be fine, I promise. We got a brand new puppy this year, as many people did, and she loves chasing the chickens. And then my second child who's in a playhouse with a goat. Yes, we have goats too. So this is a little bit, it's stuff that you don't hear about all the time. It's like, wow, mathematicians have, mini farms sometimes. Yeah, yeah, we do. We have lots of books, as you can see behind me, but we also have other things in our lives like goats and chickens and puppy dogs and lots of children. So that's a little about me. All right. Now, if at any point you find yourself having a question or you are curious about something, you have my permission to unmute and go ahead and interrupt me. I'm used to it. It doesn't bother me in the least, so feel free anytime. Or just raise your hand and then one of the organizers will call on you because I won't be able to see your hand necessarily. So just to keep that in mind. Same with the chat. I don't always read the chat while I'm going through things, but feel free to interrupt me. You have my permission. All right, now on to some math. So in 1994, Richard Guy published, I'm not even sure if that's his first series. Anyway, he published a book called Unsolved Problems in Number Theory. And in this book, it's quite a joy to read, by the way. There's a huge number of like little fun math facts that, are unsolved and unproven. And as the years go on, people prove and play with these various pieces. And if you've never pulled it out of the library, I highly recommend that you do, because there's a lot of like fun little things to play with in there. And so one of the things he talks about in there is happy functions. Actually, he doesn't talk about happy functions. Let me back up. He talks about happy numbers, but because it's easier for me to understand it in terms of a function first, I'm going to give you a happy function and then we'll talk about happy numbers. So what we're calling a happy function is going to be a set, well, and a function s, right? From the positive integers to positive integers. So you can see that here. And it sends an n to the sum of its square of its decimal digits. Okay, so what exactly does that mean? Well, we should probably do an example because why not, right? Okay, so I'm going to take a number n and my eldest daughter is 10. Okay, so this is a really cheap example, but we're going to do it anyway. So my eldest daughter is 10, and so I'm going to take s of 10, and I'm going to take the sum of the square of its decimal digits. Its digits are 1 and 0, so 1 squared plus 0 squared. Ooh, look at the math there. It's so exciting. I know it's just 1. All right, maybe not so exciting. But something, that's easy to approach. So if you pick a different number, which I'm not going to do, but you have maybe pen and paper in front of you, play around with it, see what other numbers you can figure out and say, okay, well, if I'm taking the square of its digits, what numbers can I get? Do I always get 1? Is there another number that I can get? If I repeat it and do it multiple times, is there, some sort of a pattern? And the answer is yes, there is going to be a pattern to these things. So if you repeat this s function, so repeated iterations of the happy function, or rather, yeah, the happy function, because that's what we're calling it today, does have a nice pattern. So play around with that. Okay, so again, I defined the happy function in order to give you a definition of happy number. So what is a happy number then? Ooh, I'm gonna, hold on one second. I'm gonna, forgot one little thing. Pretend that's not there. All right, there, now it's not there. All right, back to the color I won't. Okay, so a happy number is one that after repeated iterations arrives at 1. Okay, now clearly 10 is a happy number. Okay, that one wasn't so bad. So then you can do other numbers, bigger numbers, smaller numbers, whatever you like. So what if we did something like 2020, last year, for example? So S of 2020, that's going to be 2 squared plus 0 squared plus 2 squared plus 0 squared. Okay, so that's 4 plus 4. Oh, except, let me try that again. 4 plus 4 is 8. And then you can do it again, S of 8. And 8 squared is 64. And then you can do it again. Obviously, I'm not going to do this forever. And so then, like, for numbers like 2020, you wonder, like, how long will it take me to get to 1? Am I going to get to 1? Is it possibility that I don't get to 1? Do all numbers get to 1? These are all questions you can be asking yourself as you're playing around with these things. And so, as you may have cheated and saw the note below, it turns out that 2020 goes to 8, then 64, then 52, then 29, then 85, then 89, then 117, then 51, then 26, then 40. And you're like, okay, gee, is this really just going to keep going? Does this go on forever? Okay. So it turns out that yes, it does go on forever, because what happens is that once it gets, so remember we had this 2020, and then we said it went to 8, and then we said it went to 64, and so on. And then what ends up happening, that it eventually ends up at a number that leads into this cycle, right? So what was it? I think the last one I had on the previous screen was 40. And then 40, the digits there squared go into 16. And then from there it goes to 37, to 58, to 89, and then it continues on and will continue in this cycle forever. So this is what I called an unhappy cycle. It's never going to get to 1. So it's an unhappy number. And as we all remember 2020, it was a rather unhappy year. And now we know why. Now we know why. It's an unhappy number, right? Well, don't worry. There are better things on the horizon. Okay, so let's see where we can go with this. So when looking at these things, it's a uncommon question to ask then, are there sequences of arbitrary length that are that are happy? Okay, so for example, in 2020, that's not 2020, there's subtract 20 from that number. In 2000, Elsetti and Sixek, excuse me, looked at if you had written n in this form. So again, this is the base 10 representation of n, and you looked at then the happy function of that number. Are you going to be able to find an arbitrary length sequence that does give you happy numbers? And the answer is yes. That's cool. Okay, that's something fun. So that's not something that I asked about before, but these are things that people are interested in. And this is the type of thing that Richard Guy was also interested in, these sequences of various lengths of happy numbers. Can you find them? Okay, so then in 2007, Grunman and Teeple then took that base 10 expansion of an n and looked at a base b. So this is base b rather than base 10, and said, okay, well, we're going to look at base b. And not only that, but rather than looking at this square as the exponent, what if we looked at some other exponent, e for exponent? Okay, so e might not be the most logical choice in that it also represents a number in the real number system, like 2.7 something, something, something. Put that out of your mind for today, because we're not going to use that number at the moment. We're just going to think about this as an exponent. So e stands for exponent today. Okay. So it's the exponent that we have on the digits of the base B extension. Okay. And it says, yes, yes, there are still arbitrary length sequences of happy numbers for that space also. And again, happy is defined to be this set that gets you to 1. So repeated iterations of the happy function will then get you back down to 1 again. All right, so base B is cool, base 10 is cool, and these, extensions of the happy function are pretty neat. What can we do with it now? Well, Josh Carlson, myself, and Pamela Harris then decided, well, what about factoradic base? And then you ask yourself, what the heck is factoradic base? I've never heard of such a thing before. That's the first thing I asked myself. I was like, what is this factoradic? Is that a new word? So factoradic base. So we have to think about, what is this? So e power we kind of got because we saw this e power thing already. So that just means this e power here. So we have to talk about what is factoradic base. Okay, so now we get on to this factoradic happy things. So for this n, so we're starting with a positive integer n again, and we're looking at now the digits of a factorial base. Okay, so what I'm doing then is looking at 0 factorial, 1 factorial, 2 factorial, 3 factorial, and then looking at the digits of that representation of n. So let's do a quick example. So if we look at 2020, and it may not be immediately obvious, but it turns out that there's a really nice way to find those digits. So you start with the number that you want. So my n is 2020, and then I'm going to divide it by 2 and get 1010 with a remainder of 0. Then I'm going to take that number and divide it by 3, and that's 336 with a remainder of, let me pull up my cheat sheet so I don't have to worry about dividing these things in my head, of 2. Okay, all right, let me keep going. 336 divided by 4. You're starting to see the pattern here. You get 84 with a remainder of 0. Then 84 divided by 5. Don't worry, it doesn't go on too much longer, but just a little bit longer. Is going to be 16 remainder 4. And 16 divided by 6 is going to be 2 with a remainder of 4. And last, 2 divided by 7 is 0 with a remainder of 2. Okay, and you think, okay, well, this does have a bit of a factorial type thing that's going on here because you have a 2, 3, 4, 5, 6, and 7. And it turns out that these numbers, these remainders, are exactly what we need for the factoradic expansion of 2020. Okay. Again, this may not be immediately obvious, or maybe it is immediately obvious because you played with these type of things before. It was not immediately obvious to me, but you can write then 2020 using those digits. So let's see if we have cheated down here a little bit. So it turns out then, so if you look at these numbers in backwards order, so you've got 2 appearing here with the 6, then the 4, then the 4, then the 0, then the 2, and then the 0. Notice that I just kind of ignore that one. And if you think about it, because of the way that we defined this factoradic expansion, that they always have to be, the digits always are between 0 and I. If your I is 0, then AI is always 0, so that last one doesn't really do much. Okay, so you can see then that each of these digits is exactly the remainder from dividing it this way, which is pretty cool. Okay, how are we doing so far? Couple head bobs, couple thumbs up, awesome. Okay, so that's what the factoradic happy numbers look like. Whoa, did I talk about happy numbers yet? No, I didn't, did I? Okay, that's what the factoradic representation looks like. And then, as you might imagine, we can look at the factoradic happy function just defined the same way as we had seen before, with this e as our exponent. And now we're using the notation to have a factorial symbol in the base rather than a base b. And so then a happy number in this form is of something like this. So it's the one that arrives at 1 after repeated iterations of this function, this happy function. Okay, so the definition still works out. Okay, so taking a quick look at 2020 again, and now let's imagine that we're using the squares as the exponent and looking at this factorial base, so down here at the bottom, then it turns out that this is equal to 1 after just 5 iterations. And so what does that then tell us? That 2020 was in fact happy in hindsight. So all you needed to do was look at a factorial basis and then you're good. 2020 was really not so bad after all. And it ended okay and then started off a little rocky again the next year, but that's a story for another day. Another discussion. But, at least we have an idea of how these factoritic happy things work, so that at least is a bonus. Okay. So where can we go from there? It turns out that in these factoritic happy numbers, in factorial expansions, we end up having not just 1 as your possible ending point or that cycle. Remember, you either end up with, it turns out that you end up in the happy, unhappy cycle, or you end up at 1. Those are really the only 2 choices. Well, in factoritic expansions, you can end up at a different number, p, okay? P is not necessarily prime, don't be deceived, but it is a point at which you can land that may or may not be 1. Well, it could be 1, all right. But it may also not be 1. And so, for example, if you look at the factoritic expansion of 5 and you square the digits, then you get back to 5. So, well, okay, I just went to 5 and then I ended up at 5. So what do you think happens if I reiterate this one? Just back at 5. You just land at 5 every time. It doesn't go anywhere. It's just 5 all the time. So there's things that will also land on 5 eventually. I mean, the same thing happens with 1, right? If you do the happy function on 1, then you end up back at 1. And so the same thing happens with 5. Okay. So we call then the things that land at different places p happy numbers. Or in this case, this would be a 5 happy number. And so specifically, no, maybe not specifically. So there's different things that you can look at. So if you look at for different e's, so here we did 1, 2, 3, 4, 5, 6, you end up with these factoritic fixed points. So you can be 1 happy, you can be 4 happy, or 5 happy when you have a power of 2. And you can be, say, 8,258 happy if you have a power of 6. And it turns out that you don't have any cycles until you get down to this 5th power, where then you have a cycle of 2 that you can land into, or an unhappy cycle of 3 in the next one. So these are, fun things to explore that have not been done in factoritic numbers and before. All right. So the main result of our paper then was that for e equal to 1, 2, 3, or 4, the e power factoritic fixed point p of this happy function, there exist arbitrary long sequences of this e power factoritic p happy numbers. So remember that if we write n in terms of its factoritic basis, and this was our happy function, where this was the power there, then you can land on any p and have an arbitrarily long sequence for those happy numbers, okay, which is pretty cool. And so the answer to that question way back at the beginning in the history was the yes, we can do this for factoritic numbers as well. So I'm actually going to say, let's skip this for the moment. And it turns out that this result that we proved, so this is the same one as the 2 slides ago, is that this was only for e equal to 1, 2, 3, 4. But so the crutch was that there was this one part, a lemma, that really required some careful computation and some careful argument. And let's see. This is where we're going to run into spelling problems. Let me just go back one slide. Apologies. There we go. Sanchez, Garza, and Trevino recently proved that same result, that lemma that was the crutch of this thing, the reason that we only worked with 1 through 4, they've recently proved that this works for any positive integer. So they've extended it and, come up with a way to extend this result as well, which I thought was really cool. And so if you have time later today, check out some other articles on Factoradic happy things or factorial things, like the article that Evelyn Lamb wrote while I was sitting next to her on Factoradic numbers, or a card trick by Tom Edgar on Factoradic card trick. So I'm happy to provide those links if anybody would like to see them, or you can Google them. Okay, and that's where I'll end for today. Thank you.